But yeah, practice. Time for practice problems. So I will go and help with whatever people want help with for this exam. That's the idea for today's class. So there aren't too many of you in the room, but what type of problems would you all like to see?
The ones that are on the exam, please.
Yeah, I'm not going to do that.
Go over angular momentum again.
Angular momentum? Yes. So let's see. In class so far for angular momentum, I've done Goku spinning the staff and it changing length. And I did Kratos. So let me find a different one. Um, Oh, I do not think there's an angular momentum in that problem. There is not. You're gonna get the joy of watching me find things. Okay, I think this one has angular momentum. It might be too similar to the one I already did. But let me. Oh no, that's the Goku one that we did in class. Never mind. Going through old problems. And my computer is freaking out at me. And I've done that one in class already too. 6, 6, 2. Wow, I've done a lot of these. Nope, not that one. This is the exciting class you're here to see. I think there's a good chance this one. I need to read the problem. What's the tension in the cable? Nope. God damn it. Okay, I might in the end do the one I didn't want to do. What the hell is this problem? Okay, yep, I'm gonna do the one I didn't want to do initially. Because it's on the homework. So here you go. I'm gonna help you with a homework problem. I don't know if the numbers are gonna be the same or not. We'll find out. And so the general idea for angular momentum, and let me share my screen. The general idea for angular momentum is that we're going to say initial angular momentum equals final angular momentum. L initial equals L final, where angular momentum is the moment of inertia times angular velocity. When I put angular momentum on problems, it's either going to be something like I just say, hey, what's the angular momentum of this object, which I have done in the past, or it'll be based off the law of conservation of angular momentum. Conservation of angular momentum is the idea, and so I just want to make sure I'm sharing the right screen. I am. Conservation of angular momentum is the idea that if you have something moving in a circle and you apply no torques and cause other changes, angular momentum shouldn't change. That if I spin this and suddenly go and make the radius smaller, it'll go faster. Anytime you have something changing radius or mass, and due to a change in radius or mass, it changes angular velocity, that's angular momentum. Now, this problem, as I said, may look a little similar to some of you. And if it doesn't look like similar, start the homework, because this is on the homework. And this has angular momentum as a part of it. In fact, it's only part C. Would you rather I do the entire problem, or you want me to jump to the angular momentum part?
Just the angular momentum part.
Okay. So I'm going to skip parts A and B. So it says Spider-Man in a fight with other heroes snags Ant-Man with a web, while Ant-Man is at reduced size and has a mass of 0.5 kilograms. Spider-Man then swings him around horizontally at a radius of 2.81 meters at a rate of 52.3 revolutions per minute. Okay, I'm going to stop myself right there and say that if omega is 52.3 revolutions per minute, I need to convert that. Well, one revolution is 2 pi radians. and 1 minute is 60 seconds. And so this conversion will be multiplying by 2 pi divided by 60. 52.3 times 2 pi divided by 60 is 5.48. So what we're saying is Ant-Man has this mass. I'm going to call this initial because things are going to be changing. I'm getting ahead of myself, but I know where I'm going. Has a mass of 0.5 kilograms and is swung around at a radius of 2.81 meters at that speed. And going straight to part C, while Ant-Man is swinging, he goes back to regular size, increasing his mass to 86 kilograms. So I'm going to say M final is 86 kilograms. If Spider-Man does not apply any additional torques, what unrealistically small angular velocity does Ant-Man have after the size change? Assume the mode of motion of Ant-Man is that of a particle. Now, on this problem, it doesn't mention a change in radius. And if it doesn't mention a change in radius, we can probably assume the radius is the same. But what we have is he's changing mass. And due to the change in mass, what's the new angular velocity? And all I'm going to say is that initial angular momentum equals final angular momentum. Or plugging in other things, that I initial omega initial equals I final omega final. Now, when I do this, when I go and look at this, and I just saw someone else asked me to do the whole thing. I just saw the request to do the whole thing. I'll go back and do parts A and B afterwards. Doesn't really matter the order I do this problem in, but I will go back and do parts A and B. Sorry, I didn't have my chat up because when I started sharing screen partway, it disappeared. What I would do is I'll say this I here, that's the moment of inertia. And for each I, I'll just plug in mr squared. Now, in this case, all doesn't change. In this case, all initial is the same as all final. And so I can divide both sides by all, and they'll just cancel out since they're the same. That won't always be true. Normally, all changes are not m. In fact, due to law of conservation of mass, it isn't actually physically possible for m to change. But hey, comics. So I can say m initial omega initial equals m final omega final. And rearranging, that says omega final is m initial omega initial over m final, which will allow me to plug in. Any questions on that part C? Does that help with whoever asked me to do this type of thing?
Yeah, it does. Thank you.
Okay,
Yeah,
and
that
someone,
helps. Thank you.
yep, and yeah, I was wondering if you would be able because I just saw your email, so there you go. That works for you too. Now in the chat, I was asked to do the oleo parts. So let's look at parts A and B. In parts, and you know what, I'm gonna rearrange how I have this for a second, just so I can not waste paper. I want that line. Okay. In part A, it says, what's his linear velocity? Anytime I ask for linear velocity of something moving in a circle, linear velocity is angular velocity times radius. And therefore the linear velocity is just going to be his radius times the angular velocity. It's of note that you could, at this point, you might wonder which one I'm using, why I'm not using the 0.319, but to be fair, I did the problem out of order. I didn't even know that was the case yet. As the problem was written, this was the only velocity I had. Part B is asking for the tension. Now, for problems 3 or 4, if anything with a force comes up, tension, anything else, well, in general, if anything with a force comes up, you're looking at sum of forces equals 0. Oh, sorry, Newton's second law. Forces can show up in torques, so it's either going to be torque or forces, but a lot of the time it's going to be Newton's laws. And so what this says here is, what's the tension in the webbing? If I want to solve for the tension, I'm going to start with a free body diagram. What I can say is that this tension is going to apply a force pointing to the middle of the circle, although I'm in part A, so really this tension should be here and not the lower figure. And I can say that is the force in the horizontal plane. Theoretically, there is also gravity, but gravity's down and not in the same plane as everything else. And just saying F equals ma, I can say the only force is tension. And so tension equals ma. Where in this case, the A must be centripetal acceleration. It's centripetal acceleration because he's moving in a circle. Where centripetal acceleration has two equations, v squared over all or omega squared all. Now, normally I say use whichever one you know the value, but I know both here. V is 15.4. Omega is 5.48. So I can use either one. I'm pretty sure I used omega squared all. Yeah, yep, I did. Just because that's the one I didn't solve for. And so the tension will be 0.5 kilograms times 5.48 radians per second squared times the radius, 2.81 meters, which is 42.2 newtons. There's parts A and B for the person who asked in the chat. Going back at things I said earlier, on this problem, this did conservation of angular momentum, this did linear to rotational, this did centripetal acceleration. So problem 4 in this exam probably would have been angular kinematics and torque. I can make that guess. I do sometimes double dip, but not often. Like last time I showed you that I used kinematics twice. That does happen sometimes. I think I've done torque twice before, but I try not to if I don't have to. Questions on this problem? I want to turn another light on if you, excuse me. Okay. What else can I show you guys? What else can I help with?
Can you do more with ones that incorporate and finding angular acceleration?
That incorporate finding angular acceleration. Yeah, normally if we're finding angular acceleration, it's either going to be something with torque or it's going to be kinematics. Either one could be using it. Let me just see what I have here for this problem.
Can we do one with more of the kinematic side of it?
Kinematic side? Yeah, this one's not kinematics.
If you find one.
Oh, I'll find one. You just got to give me a few seconds. Let's just go back and here. I'll go on this screen. So you just want kinematics in general, or do you want it actually solving for alpha?
Solving for alpha.
Cool, got one. So this one right here. This problem says during a golf swing, you bring the club through 0.684 revolutions. Okay, I'm pausing right there. That's a theta, a number of revolutions, 0.684. But we never want to work in revolutions. Anytime I give you anything in revolutions, what you're going to want to do is you're going to want to convert that to radians. And so I'm going to multiply this by 2 pi to get radians after canceling out my revolutions. 4.2977. And what it says is I go through 4.2977 radians from where we start until we hit the ball. If the club starts at rest, anytime something's at rest, it means no initial angular velocity. At the beginning of the swing, it takes 0.220 seconds to swing the club. What is the angular acceleration? Anytime you see an equation, or anytime you give something in this chapter, if either theta is given or t is given, either one, or in this case, both, anytime those are given, that will be kinematics, where we have our three kinematics equations. Theta equals theta naught plus omega naught t plus 1/2 alpha t squared. You might notice I didn't bother writing my theta naught. It's because theta naught is always 0. Since it's always 0, skip it. Omega equals omega naught plus alpha t, and omega squared equals omega naught squared plus 2 alpha theta minus theta naught. Well, once again, I just excluded my theta naught because it's always 0. See, what I want to do is I want to get alpha. This is getting alpha using my kinematics. And I can go and play my matching game. I can say, I don't know omega. Omega was not given, nor do I care about it. And since omega was not given, nor do I care about it, I can't use these bottom equations. The only equation left is this one right above my fingers. And so I'll use that. Now, in this case, omega naught was 0. So that leaves me with theta equals 1/2 alpha t squared. I can multiply both sides by 2 and divide both sides by t squared. And I can use this to solve. Kinematics is the matching game, just like it was in chapters 1 and 2. Really more chapter 1 than 2. Oh, sorry, 2. I meant to say 2 and 3 anyways. Like in chapters 2 and 3. But yeah, if theta shows up or t shows up, that's going to be kinematics.
Thank you.
No problem. What else can I do?
Can we do some with conservation of energy and springs?
Conservation energy and springs. Yep. Let's see if I get lucky with the exam I have open.
Or even some with like where the ball is rolling down, and you got to find, or that's another question actually. Well, you got to find the angular velocity. Or
Okay.
linear velocity.
Well, this is a rolling one right here.
Oh, can we do that one?
I can do a rolling one and then I'll come back and do springs.
Awesome.
Okay. So this rolling one says Link from Legend of Zelda, and I did Breath of the Wild because it was probably more Cocoon at the time. Well, this was a year ago. Breath of the Wild was already out for a while at this point. I did Breath of the Wild because I felt like it. Places a round bomb at the top of a 4-meter high ramp in a shrine. If the bomb is a solid sphere, moment of inertia 2/5 mr squared, what is its linear velocity at the bottom? Conservation of energy, the basis of conservation of energy, is that the energy in one spot equals the energy in another. In this case, I'm going to say the energy at the top of the ramp equals the energy at the bottom of the ramp. Now keep in mind, energy has 4 different terms. There is linear, that doesn't work. There is linear kinetic, there is rotational kinetic, there is gravitational potential, and there is spring potential. When doing these problems, you almost always need the linear kinetic and the gravitational potential. They both basically always come up. But the other two only sometimes do. This one right here only comes up if you have something rolling or moving in a circle. This one only comes up if you have a spring. And this problem that I admittedly are covering right now does not mention springs. And since it does not mention springs, I'm not going to include the spring part. I'm just going to say energy is linear kinetic plus rotational kinetic plus gravitational potential. And at the spring, which I could sometimes add, I can add it like in very faint yellow, that's not going to be here because there is no spring. Yellow pen barely shows up. And what I'll do is I'll write an equation for the energy at each spot. See at the top, he says it places the round bomb. I didn't actually say it has no kinetic energy up there, although I guess I should have been more direct, but I said he places it. So it's just sitting there. The energy at the top is just mgy. At the bottom, it's rolling. At the bottom, rolling means that it's doing two things at once. Something rolling is moving linearly, 1/2 mv squared, but is also spinning in a circle. And so I have both those terms. Now, keep in mind, I want to solve V, but V and omega are related. Thing is, I know omega, something I covered earlier on. Earlier on, I said V equals omega O. Rearranging that equation, what that means is that omega equals V over O. And that moment of inertia I, that was given in this problem. I said for a solid sphere, I equals 2/5 MOAR squared. And I'll plug those values right in. I don't know why I did capital R though. Sorry. So let's look at this. This is 1/2 mv squared plus 1/2 times 2/5 is 1/5. V squared, V over R squared, same as V squared over R squared. This allows some R squareds to cancel out. And I get 1/2 mv squared plus 1/5 mv squared.
Wait, 2/5 plus times 1/2 is 1/5?
Yep, the twos cancel out.
Oh, okay.
Now, when I do this, I like to sometimes just reduce here, 1/2 plus 1/5. There's a bunch of ways I could do 1/2 plus 1/5. You could just do it in a calculator if you wanted, but I'm just using a common denominator that 1/2 is the same as 5/10, and 1/5 is the same as 2/10. And so therefore 5/10 plus 2/10 is 7/10. And so 1/2 plus 1/5 is 7/10 mv squared. But now that I know that, I'll use my conservation of energy. E top equals E bottom, or mgy equals 7/10 mv squared. Where I can multiply both sides by 10, divide both sides by 7, and divide both sides by m. And I get V is the square root of 10gy over 7. Quick thing. If I happen to give a sphere rolling down a ramp, and the first thing you write down is the square root of 10gy over 7, you're not going to get many points. I do want you to show all work. If I do a rolling down a ramp problem, won't guarantee I do. I don't remember what the problem is off the top of my head. I want to see the work. That's what I care about. Because the way I grade with partial credit, if you give me an answer and no work, you'll only get the points for the answer. So make sure if you're doing these, you show the work and how it got though. But either way, I can plug in my numbers. 10, 9.81, 4 meters. 7 square root of 7.48 meters per second.
And that's our linear velocity.
That's your linear velocity.
If you asked for a angular velocity, you would have given us the radius, right?
Yeah, I'd have to give the radius because
Okay.
you wouldn't be able to solve it otherwise.
Okay.
Any other questions here? Okay, so you also asked for a spring problem, right? So in
Yeah,
class,
conservation of energy.
in class on Monday, I did a spring problem that was pushed to the right. I did the Smash Brother Ohms problem.
Right, from that first exam? The last exam?
From the last exam, yeah. So I'll do a conservation of energy with springs that's up and down instead.
Yeah, that's, please, thank you.
And ooh, that was surprisingly complicated. Oh, nope, that one's not up and down. That's the Luffy one you had on the homework. Oh no, Luffy one was in the class. Luffy one's in the class. No, let's go to this semester. Sure. Sometimes I run out of ideas. Yeah, I actually messed up and wrote the wrong semester on this exam. I sometimes run out of ideas and I go very obscure video games. As demonstrated by me giving you a secret of mana question last exam. As I was writing the exam, the semester this came up. My wife was playing this game though, and I kept watching it happen. So, there's a game called Kingdom Hearts Birth by Sleep. I have no idea off the top of my head where it falls in the Kingdom Hearts series because the series is dumb. But I think it's one of the first chronologically. But there's a part where one of the main characters, named Aqua, is put into a large ball and enters a pinball machine. When Aqua enters, she steps onto a spring which compresses 4.8 meters. The spring then launches her 12.5 meters upwards. What is the spring constant of the string, and what is her velocity at the figure B there? And it says her mass. Now, she is in a ball. And so since she's in a ball, it would seem logical to talk about rotation and things. But I don't mention rotation. I just say she gets launched upwards. Basically what I have is a spring. She's pushed down onto it, and then she gets shot up. I'll go back further so you can see it. It's just pew. That's all it is. There's no rotation here. And so if I'm going to do energy, I'll say my energies in general will be 1/2 mv squared plus mgy plus 1/2 kx squared. In this case, I am not going to include rotational because we're not talking about rolling. We just have something being launched. And I'm going to include springs because I have a spring, in this case wearing a huge boxing glove. It was real hard to get these screenshots. So what I can do, and you know what, can I make that a little bigger? So what I can do is I will go and figure out what I know about each one. Now in this case, she's going up and down in Y, and the spring is being compressed up and down in Y. So what I'm going to say is they're both in the same axis. Instead of 1/2 kx squared, I'm going to say 1/2 ky squared. The problem we did on Monday, I did not do that, right? Because someone was being pushed against something horizontally and being flung downward. But this one, everything is up and down, so I'll keep everything up and down. And what I'll do is I'll figure out which of these terms are what where. Now, for gravitational potential energy, you define your 0 point. But for spring potential energy, you don't. Spring potential energy is wherever the spring isn't compressed. This is 0. If I push this down, that's not 0 anymore. And so I have to say that the height is 0 at point B. Because that's where it's not compressed. If that's true, that means my height at A is below my 0 point. So my height at A is negative 4.5 meters. Negative because I'm below the point. And my height at C is 12.5 meters. We're also going to talk about velocity at various parts. And it says, when Aqua enters, she steps on the spring, which compresses 4.5 meters and launches her upwards. Well, let's think about this. If she goes on this thing, and that's how as far as it compresses, then pushes her up. What is that? Its max compression? That's when it's in between going down with a negative velocity and going up with a positive velocity. That means her velocity at A must be 0. Using the same logic of why her velocity at C must be 0. That her velocity at her highest point is 0 because that's when they're in between going up and going down. Her velocity at A is 0 because she's in between going down and going up. As for velocity at B, we don't know it. I asked for what is Aqua's velocity as she passes through the spring's equilibrium position. So now that I have that, I'm going to write 3 energy equations, one for A, one for B, one for C. And say my energy at A, V is 0, so that term goes away. So it's mgya plus 1/2 kya squared. My energy, let's color code this. My energy at B, I have velocity here, 1/2 mvb squared, but look at y at B. Y at B, focus, y at B is 0. And if y at B is 0, both these terms go away. That just leaves my energy at C. At C, my velocity is 0, so this term goes away. And logically, I should have this ky squared term too. But let's just look at the spring. The spring isn't doing anything at C. Once this gets launched up, the spring is just still sitting there. And since the spring isn't doing anything at C, I'm not going to include it. Now that I'm set up, I can try to solve. You see, what I know is the energy at all points is equal. The energy at A equals the energy at B equals the energy at C. And this problem asks for 2 things. It asks for, in part A, what is the spring constant of the spring? Well, when I look at this, the spring constant of the spring only shows up in A. So I'm going to use my energy at A. And I know everything about C. So I set that equal to C. And I'll just say mgya plus 1/2 kya squared equals mgyc. If I want to solve for k, I'll subtract mgya from both sides. I like to factor out my mg's, although that step is not necessary. I'll then multiply both sides by 2. And divide both sides by ya squared. Wow, I made her really light. Okay, this isn't working. I'm just gonna plug in those numbers again. 2 times 65.3 kilograms times 9.81 meters per second squared times 12.5 meters minus a negative 4.5 meters over a negative 4.5 meters squared equals 1070. Part B says, what's the velocity at B? To get that, I'll just say my energy at B equals, instead of equal to A or C. I like to use C because I'm a big fan of keep it simple, stupid. That when in doubt, use this equation over this more complicated thing. And so I'll say 1/2 mvb squared equals mgyc. I'll divide both sides by m. Multiply both sides by 2. If I go slow, I can do it.
It's going off the screen.
Oh, I didn't. It is still on the screen for me.
I can't really see it.
Okay, we're gonna have to lose some of the top stuff. I'll come back to that in a second. And then
Okay.
square root. I'll move it around in a second so I can show everything. Stay. There you go. Just had to zoom out a little bit. And so if you have a conservation energy with a spring, follow it the same logic as conservation energy rolling. Energy at the one spot equals energy at the other. It's just what's going to change is you're going to have to go and include a new piece of energy. And when you include that new piece of energy, just write an equation for the energy at each spot and start canceling out. Questions? Yeah, I think both by sleep one might be one of the more obscure. Like Kingdom Hearts isn't obscure, but both by sleep definitely is.
Thank you for doing that, bro.
Oh, no problem. So what else can I solve for you? What else can I help with? I mean, I can, instead of doing problems, just try to say other things about that'd be helpful too. But what would people like to see? Another test question, please. Okay, I can see that. What type of test question? Do you want to do like more energy, more momentum, more rotational? I mean, these are all test problems. Every single one I've done today is an old test. So if you would be slightly more specific.
Have we gone over like a problem for every question?
We haven't looked at any momentum today.
Can we do that?
So last class I did a momentum problem that was, oh sure, we'll do this one. Last class I did a problem that was completely inelastic? No. What did I do last class? I legitimately don't remember what I did last class.
With you did with the Spider-Man and the bird.
Yeah, Spider-Man and Vulture, which they bounced off each other. Okay, so last class I did one that was completely I did one where they bounced off, where the two things came in and went off, but side to side. It was up and down. This one is the same thing, just side to side. You know what? I have enough time. I'll do this problem and then I'll do a completely inelastic one. Basically, just doing this one because I happen to have it open. But after this one, I'll do a completely inelastic. And so what it says is during Avengers Endgame, there was a scene, I want to shrink this a little bit so it fits better. During Avengers Endgame, there is a scene where Thor's hammer Mjolnir is thrown in the air to deflect Captain America's shield, which is also thrown. This gets really hardcore into spoilers. It was pretty new at the time in 2019, so I didn't go into any more detail. Side note, writing this exam, I watched this scene over and over again. It is so dumb when you watch it slowly because, like, it shows something moving one way and then it just cuts to it moving the other way. Like, Captain America's shield in that scene, if you watch it, has a mind of its own. Like, it's thrown this way and then it shows it going straight up. It makes no sense. But anyways, I ruin movies for myself. Let's say that Mjolnir is traveling at 23 meters per second and the shield is traveling at 15 meters per second in the opposite direction. So we're saying initially, the velocity of Mjolnir initial is 23 meters per second. And the shield is initially traveling at 15 meters per second. But it says in the opposite direction. If I look at my diagram, it shows to the left. The opposite direction means I need to make that negative. After the collision, Captain America's shield reverses motion and moves at 16 meters per second. And now it's to the right. What velocity, magnitude, and direction is Mjolnir? I don't know why I just did a W. And I give the masses. The mass of Mjolnir is 20 kilograms. Why do I have that memorized? And the mass of the shield is like 5.44. Seriously, I do too many problems with, well, me and comics. You can see it in the background, but I do too many problems and I start memorizing this shit. This is a collision. Any type of collision would say initial momentum equals final momentum, where momentum equals mv. And what I'll say is the initial momentum is going to be the initial things happening. The mass of Mjolnir, the velocity of Mjolnir initial. And the mass of the shield, the velocity of shield initial. That's my initial. After the collision, they're both still moving. The mass of Mjolnir, the velocity of Mjolnir final, plus the mass of the shield, velocity of the shield final. Just my initial momentum equals my final. Now in this one, I want this term right here, the velocity of Mjolnir final. So I'm going to solve for this one. What I'll do is I'll subtract this from both sides. MMVMI plus MSVSI minus MSVSF equals MMVMF. Now I can divide both sides by the mass of Mjolnir. Well, I'll just divide this by the mass of Mjolnir, and I'll divide that by the mass of Mjolnir. Me being lazy. And plug in. Now I got a positive answer, so that means it's 14.6 meters per second to the right. Positive is to the right, negative is to the left. Or positive is up and negative is down, depending on which way you're going.
Can you write out the points that they would get for that?
I don't have how I graded it last time on me. But if I had to guess how I did it, I probably did 5, 5, maybe 5 here. This negative sign is up probably either 2 or 3, 5, 10, 15, 16, 17. Maybe 5 for the answer, and then 3 for the direction. That would be my guess. As I said, I don't have my grading rubric on me.
Okay.
Now it is possible instead I do completely inelastic. If I do completely inelastic, that means the things are going to stick together, or possibly they start stuck together and split apart. Of course, I instantly find a completely inelastic one that I've done already, so I don't want to do that one. It's no fun to do ones you've seen before. So if you give me a second, I will find one. Sure. You know what? Since we just threw Myono, the first one I found, this is just complete coincidence that the first one I found, is instead of throwing Myono, let's throw Stormbreaker. I have a type. So it's just the first one I found. So this says, Thor leaps forward holding his axe Stormbreaker, then throws the axe. Before throwing Stormbreaker, both Thor and the axe are moving at 8.94 meters per second, as shown below. If Stormbreaker leaves Thor's hands at 150 miles per hour, okay. This is from a final exam. On the final, I worked in unit conversions again. I probably won't work unit conversions into this problem on this exam. I probably won't. But real fast, I say the velocity of Stormbreaker final is 150 miles per hour. If I want to convert this, 1 mile is 1,609 meters, and 1 hour is 3,600 seconds. And so that value right there is 67.0 meters per second. So if Stormbreaker leaves Thor's hands at 67 meters per second, what is Thor's velocity, magnitude, and direction after the throw? This is a completely inelastic one. It's a backwards one. Normally completely inelastic is they start apart and go together. If you go back to the chapter 6 example problems I did on Friday of that week, there is Spider-Man catching a call. That's the one I opened and said, I already did this one. So it can go that way, but it can also be they start together and come apart like this. I'm still going to say initial momentum equals final momentum, or momentum equals MV. It's just now I'm going to go and change my initial condition a little bit. In this one, they start together. And so in this one, since they start together, I'm going to view my initial as one object. The mass of Thor plus the mass of Stormbreaker, they're both moving with some set velocity, that's VI. Instead of saying MV plus MV, I'll just treat them as one object. And that'll equal the mass of Thor, the velocity of Thor final, plus the mass of Stormbreaker, velocity of Stormbreaker final. If I want the velocity of Thor final, I'll subtract this from both sides. And divide both sides by Thor's mass, which, if I remember correctly, is stupidly large because it's always put as stupidly large. No, actually, it's a pretty reasonable number though. I must have used Helmsworth weight. So 114 kilograms plus 27.2 kilograms minus 27.2 kilograms times 67. Oops, I messed up. I will fix my mistake in a second. When I did this, I dropped this VI. Like I just didn't put it there. There should be a VI here, which was 8.94. So I apologize for that. And so I got a negative answer, so that means it's 4.91 meters per second to the left. I know it's left because I got a negative value. That when he throws his axe, he's gonna go pew and go that way. I kind of like that I had an Infinity War question and an Endgame question today. Makes me kind of happy on some level. Okay, it is 2:50. I'm actually a minute over, so I am going to stop there. Any other questions, feel free to email me. I also have office hours at 3 o'clock to 5 o'clock, or 3 to 4:50 today. But I will stop there. Hopefully this somewhat helped. Have a good day.